Perfect. Morning, everyone. Thank you for joining us today. This is the fourth webinar on the internationalization for the UKRAS network. Thank you, everyone, for joining. We've got today, there's Jacinto and myself running this series. And then we've got three guests from around the world. This time we've got Francois Pomereux from Canada, from the Northern Robotics Laboratory. Is a research chair in the field robotics. Then we've got Professor Maurice Fallon, from Professor in Mobile Robotics from the Oxford Robotics Institute. And then finally from Australia, we've got Professor Carl Sammut, Professor of Maritime Autonomy. Today the topic is extreme environments. So we're going to have three sort of presentations about the topic, and we can see sort of what research happens around these three different countries. The idea is to sort of meet people from different countries and trying to improve networking and sort of the connection that we can have, the UK has with Australia and Canada. We're going to have about 10 to 12 minutes for presentation each, followed by 5 minutes for question per speaker, and then we're going to have a final panel discussion. I think we can just get started immediately with Francois, if you want to start sharing your screen. And people, feel free to put your question in the chat.
All right. Thank you for the introduction. It's my pleasure to be here today to talk about autonomy in extreme conditions. I use Push the Boundary through field robotics. I want to explain shortly what is field robotics for people who doesn't know. This is where we go outside first, try a system that claim to be working, list what is not working, then go back to the lab and tackle those challenges instead of doing the regular way, which is working on math and then trying out if it's working. So today my goal of the talk is not to go deeply into our research, but to explain the motivation of why we are doing that and how we are doing it, at least in my lab. So let's first start with that graph. There's actually an institute tracking the occurrence of extreme events in the world. And here I only focus on extreme temperature and storm. And we see that climate change is clearly having an impact. And we are growing the number of these events. So I would argue that it makes sense to plan future system or future vehicles that need to handle this change beforehand. On top of that, it's not that they are going lightly, it's that those extreme weather are costly. And here's, at least in the US, the number I could find is that the cost of recovery was 10 times more from 1984 to 2024. So I'm not a businessman. I'm not saying you that there's a market of $150 billion here. I'm telling you that there's a problem of $150 billion. When I was looking numbers for Canada, at least in 2024, that was raising at 5% of the GDP to recover from extreme weather events. So what does it mean, extreme weather events in Canada? Because we have a specific location to deal with. Here we see a map of the world seen from the top. On your left, you will see Canada, and on the bottom, you will see UK. And the big red line that we see over here is the 50% extent of the chance of having a snowstorm. The tiny green one would be the max extent. So it's unlikely, but you can have snow over here, and you have 50% chance of having snow if you're on that red line. So in Canada, what it means that for 60% of the territory, which is a lot inhabited, so clearly there's a lot in the Arctic Circle, there's snow at least 6 months per year. So clearly, snow and snowstorm is an issue or something to handle on our side. Without going too much into defense, also the Arctic Circle is melting, which open trade route for boats, which triggers some safety issue on what's going on north. So adding vehicles that can handle extreme weather and snow and ice is actually of importance in Canada. What does it mean, extreme events? So I had a couple of examples. I will focus on one that happened recently. In 2017, there was a flash storm over Montreal, 75 centimeters of snow in 3 hours. That's a very high rate. 300 people were blocked on the highway, and even the safety vehicle. And we're used to snow, by the way. It's not like the whole province get blocked when there is snow. But even the emergency vehicle were getting stuck on their way to actually help people, which means that people were waiting for 8 hours in their car. We had also extreme events that had imply freezing rain, where it shut down the power in at least in Quebec City for a couple of weeks. So those events happen, and actually being able to have proper emergency vehicle or program system is useful. So what it means for us as roboticists is that we need to design and develop systems that have those events in mind. So even now in construction, they ask you to take the margin of the weather, for example, but now to also plan that you need to have margin for the slope of the event. So you need to plan ahead what it needs, which means better adaptations. For the public, it will also mean that any robotic system will have a better acceptability. We see that those events are hard and we can improve civil security. And in general, we cannot claim that we'll deal with productivity if our system are fragile or if our solution are fragile. So it will also help on that side. So to focus on those issues, I created the NORLab Robotic Laboratory with the mission to explore the complex relation between robotics and adverse environments. So the theme of that webinar fit extremely well, so that I changed the mission for it. So I'm very happy to be here. How do we handle that? So here's a map on the top left. This is the location of my University Laval. And we are lucky, so we are in Quebec City, and we're lucky to access a research forest, which is the size of, I think, 4 times the urban area of Paris. That research forest has a very specific feature, which is one of the shortest area being considered a subarctic climate. But it's a humid subarctic climate, which means that it's getting very cold. But there's always snow. So 6 months per year, there's snow over there, and there's actually 6 meters of snow falling on the territory every year. So for us, it makes a very nice testing location where we're not scared to have snow or not during a year. We also regularly, so we plan 4 weeks, a full week of deployment 4 times a year during winter over there. So my whole research team sleep there. We have a cook, and we test our system 4 times a year over there. What type of vehicles or robotics we're focusing on? We're mostly focusing for now on ground vehicle, unmanned, and we have access to a mobile lab, which has solar panel, and we can tour in remote territory. It's essentially a garage with a control station in front, packed with batteries and all of the equipment to repair our robots. And we tend to do a lot of refueling missions and investigate what's the relation of weather when we try to reach out, for example, a faraway cabin in the wood, and then do that back and forth for a while. All of the research is, of course, based on a large research team, for which I'm thanking them for helping out. The lab has three major trusts for research. So the first one covered the project Snow and Cryonic, and this is where with defense partners and the power industry, we do a lot of long-term navigation in remote forest. For the power industry, what they like about it is to be able to do inspection in remote area. Because in Quebec, the power is coming from up north. We have huge dams that are there, and then we have power lines that need to bring the power. And every time there's a couple of kilometers, you need to lower the voltage, and those are called substations, and they are considered critical infrastructure for the country. They need to be inspected regularly, but they are in remote location. So having robots that actually can stand there, and it's very useful. And what makes sense is to actually do the inspection during a storm instead of after. So for them, there's very high value of us investigating how to navigate during those particular events. We have a line of research in AI for forestry, and we do also search and rescue mission with defense. Search and rescue, yeah. So a very quick glimpse at what we are doing for forestry, because it's not the goal of that talk. We're mostly focusing on machine learning and vision to detect trees, to go actually beyond just detecting if it's a tree or not. Now we want to know the species, the size of the tree. Essentially, we want to go toward precision forestry, whether the machine should cut it or not, and try to bring back the information to the cabin of the operator. This track of research is led by Philippe Giga, which is the other prof in the lab. We were also heavily invested in the DARPA Sub-T challenge, where we perform actually quite well given the how young was the lab at the time, which trigger also some specific mission with defense about nuclear inspections right after. But if I go back to the focus of the talk, which was more around ice and snow, so in 2022, published a high-level paper on the challenges of deploying robotics in the cryosphere. So what is the cryosphere? It's the place on Earth where you can find water at a solid state. And here we see the sort of the high view of all of these places, going from ice cap, glacier, snow cover, permafrost, ice sea, ice shelf, and glacier. And there's clearly a relation with latitude and elevation to find those locations. When we do a quick survey, there was a lot of push, mostly funded by defense early on robotics. And this is the type of research that spawned actually the field robotics as a subfield, which was interesting to oversee. And where we are positioning ourselves within that is that essentially since 2021, we're continuously deploying on frozen ground and snow cover. With the Cryonic projects. We were invited by NASA GPL on the HIL mission. We went to Alberta to test our localization system on Glacier. And in 2 months, our team will be deployed in the Arctic Circle with the Operation Nanook, where we'll investigate the challenge of localization in Arctic steppes. Which is just imagined as an open desert that is white, which is quite challenging for localization. A very high level overview of what we do in terms of research. I will not go into detail, but we cover perception, traversability, and motion to controls, because we need to have essentially to master the whole stack to be able to deploy an app system that move around. And what does it look like when we deploy? So here's our first 20 kilometer of autonomous driving in a remote forest, where we could show that we can navigate during day and night, during a storm, snowstorm, rainstorm, and so on and so forth. I will go a bit faster. This is our campus. That's a Wednesday for me. This is what it looks like when I'm going to work. But where we are going in terms of ongoing challenges, is that we are hunting blizzard events. And we can see here what is the impact on a LiDAR system. But most importantly, is that blizzard compared to snow falling, which is okay. It's white, black and white noise that we can filter, but blizzard is an attack of particle in the given direction, which actually perturb quite a lot the localization system. We'll go a bit faster, but this is where the typical challenge that we are facing in our forests. And what I'm aiming now is to have autonomous snowmobile that is able to do complex maneuver in snow, which is a bit what we see in the bottom right as an example. And that's it. So I was trying to squeeze it on time. Hopefully it didn't go too far. And while I'm taking question, here's our pre-release for a full year of deployment in the Forum around Sea, where we actually recorded a lot of high quality data. And since we're in pre-release, it's a good way to advertise it. Thank you.
Perfect. Thank you very much, Francois. That was really interesting. I love that in Canada, just walking to work it counts as an extreme environment. That's really fun. So yeah, the questions open. Let me check if there's any question in the chat. Yeah. While we wait for people to ask questions, I've got one myself. So, one sort of a common theme in robotics, a list in industry is the use of simulation, quite a lot of simulation to sort of plan your work and simulate the environment, and then in a safe way just test and plan your motions in a safe environment. But I'm assuming when it comes to extreme weather that those are really, really tricky to simulate. Do you use it at all?
It's a very good question. We have that, so we don't do simulation at all. We used to investigate that. So for the forestry, for example, which is a bit more control in terms of perception and vision, but it was so specific what we were looking at that the students spent at least a year or maybe a year and a half developing the simulator for a specific case. And instead of just going outside and record the data. So we were not sure about that direction, but where we trigger is that modeling snow is super hard, and we are far from offline. The type of challenges that we are facing is high drift, weird configuration of the terrain. I didn't go into details, but when snow falls, it doesn't fall uniformly. If there's a small tree there, the robot might drop. Actually, and all of those things, you will never see it in simulation. So the way I lead the lab is I prefer to have them on site for a full week, play with robots, understand what's the limitation, and then work with that knowledge instead of trying to simulate that on their computer. So essentially, I prefer my software engineering to be outside instead of developing software. But it's not for everyone, and it's very specific. But we are targeting also exploration, so places where you have absolutely no idea what you will find. There's also a shortcoming of simulation. I think I saw some.
Yeah, I think we've got a couple of questions in the chat. I think we've got Andy's first is asking, what are the approaches you're taking to try and overcome the blizzard localization challenge?
Our first step is to actually record those events. So unfortunately, they are on the long tail of distribution. And right now, I show you everything I got. So we have few examples, and we know that they are critical. Where I'm going with that is that I'm building at the research forest a continuous deployment site where the robot will just continuously go out, and I hope to hit those events more often. It's just that right now we see a snowstorm, the team try to get set. By the time they pull out the robots, the snowstorm is done, and then it's always like that. So it's actually very difficult to record. So I don't have particular solution except dealing with localization and filtering out properly. But where we are is that identify really the problem by gathering a larger data set of those events instead of having regular data set and only few of them in it. Yeah.
I think I'm gonna ask Peter's question first because the other one I think is quite simple. You can just probably type in the chat later on what the other robot is. So Peter's asking, how do you address ephemerality and slow change in the environment when localizing and mapping?
All right. With that data set, we start to actually get metrics on how to do multi-seasons localization. So the students right now evaluating it, we realize that there's actually very few SLAM solution that can reuse a map and then really relocalizing it. So what we're discovering is that you can load a map, but then it will start to do its own map and localize in the new representation. In our pipeline, we essentially, in real time, we are identifying if we see through an object or not. And if we start to see through and if we accumulate observation, we'll lower the probability of that object to be static. So all of the points in our 3D map have a probability of being static. And if that probability goes too low, we remove them from the map. But this is by the way, it's my PG old solution. It's just that it still works and we can go through a lot yet.
Cool, perfect. I think there's another question for Jacinta, and maybe if you don't mind, you can answer that on the chat. But just for the interest of time, we should probably move on to Maurice. But yeah, thank you very much, Francois. That was really interesting.
My pleasure.
Okay, shall I go ahead?
Yes, please. Yeah.
Okay, so can you see my screen?
Yes, we can.
Okay, I'll just keep track of time as well. Okay, so my name is Maurice Fallon. I'm a professor in Oxford Robotics Institute, and I work on multi-sensor mapping and navigation, quite adjacent and similar space to Francois, except not nearly as extreme. South of England isn't prone to such extreme weather. And I'll talk a little bit about localization mapping and then demonstrate what we've been developing in some applications. A lot of it has been focused on legged robots, but it's not necessarily legged robot specific, but Spot and the Animal robot that we work with have a variety of cameras and LiDAR and onboard compute that gives you a variety of challenges. And also motivated by the DARPA Subterranean Challenge, or developed during the Subterranean Challenge, is our multi-sensor pipeline called VLANS, which combines visual tracking and LiDAR tracking into a redundant motion tracking system. So where camera tracking systems tend to fail in dark environments, and LiDAR struggles in long featureless tunnels. The fusion of these modalities can avoid underlying failure modes of the individual sensors. And our approach is to fuse those together using a factor graph approach, where least squares cost functions are used to fuse together different contributions from the IMU sensors, planes detected in LiDAR, edges, so door jams, for example, detected in the LiDAR, and visual features that are tracked over time, and then optimized using sliding window optimization, for example, using GTSAM. Actually, a broader version of our system also uses ICP-based constraints, which uses actually lib point matcher from Francois' team, which is still being used in our group. And this video gives an overview of one of the Animal robots that we developed within our contribution to one of the DARPA Sub-T challenge teams, called Cerberus, mapping an underground mine that's located near to Bath in a town called Corsham. And you can see top-down view that shows high accuracy tracking of the position of the robot with respect to ground truth. So since then, we sort of integrated that mapping system within a modular mapping device that we call Frontier that can be attached to any robot. And in particular, the next part of my talk, I'll talk a little bit about how we've developed an autonomy system for the Spot robot. I guess this video just shows some results from mapping separate from our robot actually handheld in this case. So yeah, moving on to the kind of the first application of this work of industrial inspection. So we've done a lot of testing in an analog site called Fire Service College, which is located in Corsham, which is a town in the west of Gloucestershire. It's a mock-up test site for firefighters. So you can see it's got a variety of staircase challenges, unlit rooms, and trip hazards. And we effectively developed and built out the autonomy system for the Spot robot. You can see here, the first phase of the autonomy system is to build a map using the SLAM system that I talked about. It's been teleoperated by an out of line of sight operator using the map as a prior some prior information, and they're building up this prior map that will later be used for autonomy. So after moving through multiple floors, you can see here that the site has maybe three floors. It's usually used to test. It's usually filled with smoke for firefighters to train going into smoky buildings, but none of those specific hazards were activated for this. And you can see in the bottom left kind of a 3-floor map of the facility as the Spot robot sort of finishing its operation. And I guess this pull away kind of shows the multi-floor map. So then using basically the highway that the robot operates on, my colleague Nick Hawes and his PhD student Michal Stanska developed a mission planning system. So we use the highway that the robot kind of identified during the teleoperation phase, which then forms the route that the robot can travel upon using an autonomy system. So we transform the SLAM graph into a topological map of nodes and edges, and simplify it so as to drop out edges that are mostly linear or don't involve any particular maneuvers, as well as identifying, I don't know if you can see in the image, but there's some edges here in blue which are staircase climbing edges, and green which are traversals through narrow doorways. So those require a different autonomy interface with the Spot system. And then effectively there's a state machine which can traverse from node to node to carry out a mission. And Michal and Nick's particular focus is being able to incorporate more rich information into that. For example, to be able to plan missions that go to a series of inspection points and also consider battery life, so that the robot can, for example, carry out a set of inspection coordinates, minimize risk, and ensure with some probability that the system will be able to return home to a docking station. And this kind of shows a robot's eye view of the robot going from node to node. I think this one here is walking up a staircase, and then it starts moving around the outer part of the Fire Service College test site. In 2024, early 2025, we carried out a large-scale deployment of this system in the jet reactor facility in UK Atomic Energy Agency, where we worked with colleagues in the race unit of UKAEA to deploy the Spot for an extended period of time, carrying out autonomy inspection missions. So this is a view of it's probably doing very badly over Teams, but I'll just skip through it. So the robot moving from inspection point to inspection point around the site, pointing a pan and tilt camera and a thermal camera at different industrial equipment, and use this to sort of demonstrate the capability for long-term deployment. And as illustrated here, the robot starts and ends each mission at a charging dock. So interesting when you start moving to sort of long-term operations. The missions themselves quite short, but the real challenge is that we did this for over a month, and we're carrying out multiple missions per day. And then we really start to get a view on the sort of long-term operation statistics of the system. So the goal was to collect visual images and infrared images at different locations around the site, to measure temperature and humidity and log those, and also to identify hotspots of change. This is 3D changes illustrated here. And we got a view on what are the long-term statistics of operation. In particular, the vast bulk of missions were successful. Some of them required a human operator to approve an action where an edge transition on the graph was a failure, and some of them required actually failed out. And main reasons for interventions were malfunctions in the spot payload. So the interface we have to actually command the pan and tilt unit on the top of the robot. Basic things like overfilling a disk when logging data. And then we had a particular issue with one of the tools that we're using to monitor the status of the robot was actually breaking the autonomy system. But you only get to really learn these kind of challenges when you deploy at scale and go to this commitment of long-term autonomy. Here you can see some images from a different field trial showing the repeatability of image capture from the RGB image and the thermal camera, showing that despite going back on different days, different times of the day, that quite repeatable images can be acquired. I don't have time to talk about another mission that we did to deploy the Spot robot under a decommissioned nuclear reactor within a crawl space where the usual inspections are carried out with full hazmat suits. But this is another use case that we explored with NRS, which is the National Rehabilitation Service for the nuclear sector. So moving on to talk a little bit about forest robotics. Again, not quite in the extreme environment that Francois is familiar with. We've had a multi-year EU project with a number of partners from Switzerland, Germany, and Finland to develop both drones, legged robots, and an autonomous harvester in ETH to move towards a more digital workflow for forestry. And while this is maybe not even a particular challenge for mobile robots, this video is just to show that legged robots are quite mobile in forest environments and can be used in a number of realistic challenges to carry out inspection patterns. So effectively, we developed an autonomy system that allows the robot to carry out a lawnmower pattern or in and amongst a plot of trees, and it can make autonomous decisions to plan local routes and to avoid obstacles or hazards. So here you can see a video showing the robot moving around through following at a high level a carrot that's illustrated in the video. Here you can see some challenges where the robot's not able to determine to go left or to go right around a particular tree, but after a while it becomes unstuck and continues in its operation. There's a fallen branch here that it's working its way around, and eventually it's able to carry out this entire inspection mission. Meanwhile, on the same system, we have a secondary processing system that's using the output from the laser slam system to map the terrain of the terrain of the environment, to extract each individual tree, to measure the diameters of the tree, and to measure the heights of the tree. We also should be working towards species detection, which is something that Francois mentioned. Lastly, I'll just finish up by mentioning that we're currently jointly running a 3D mapping challenge with Hilti and Trimble that's using 3D head-mounted wide field of view cameras to do visual SLAM. and visual localization. And there's an ongoing challenge at hilti/trimble/challenge.com, and it will have a finals at UKRAS in Austria this year. Okay, so I'll finish up with that, and happy to take any questions.
Brilliant. Thank you very much, Maurice. That was really, really interesting. As usual, people, if you've got any questions, please type them in the chat. I might just start with my first one, just to break the ice. So yeah, that looks really, really clever. And my sort of question is, when it comes to sort of an inspection of a nuclear factory or nuclear field, you probably, the most interesting operator would be, or the most useful operator would be someone with expertise in nuclear rather than robotics. So how easy it is to just hand over the robot, let's say the animal or the spot robot, to someone who's got very little expertise of robotic itself, but just there to inspect the nuclear facility? Can you just hand it over and then the robot, it's very easy to control, or is it still requires a very well-trained operator?
I mean, I guess it's not really about the robot, it's really about the software interface.
That's what I meant, sorry. Yeah.
So, and we have made a couple of copies of our system for commercial collaborators. So we are working to improve the user interface, but things like using RViz and RQT-based modules that you can build around RViz is poorly received in a commercial environment. And if you were to compare our system directly to Boston Dynamics, who were involved in one of the trials that I mentioned previously, and under the reactor one, I mean, there's a huge amount of work that Boston Dynamics have put in to make the spot autonomy system that they develop user friendly, simple to operate, because the more, like I guess our focus is more on developing more complicated autonomy that can do more interesting decision making, but then trying to transfer that complex decision making or the complex system that's more of a research grade to commercial users is a challenge. And really, when that system is so complicated and there is any particular failure mode, like some of the things I mentioned, really that's going to highly undermine general confidence in your system, even if it's, for example, an environment where you're operating out of expected conditions. So I think the development has to be done in a sort of iterative manner where you're working with maybe an understanding commercial deployer. Like UKRAS sits between commercial and research, and they're really been helpful for working with us to give us feedback and to support the systems. I mean, the things, maybe one thing you don't see is that I mentioned this 35-day autonomous deployment, but it's in an active nuclear research site, and there was a human operator that had to have line of sight visibility at all times. So the steps that you take to move the system forward to being deployed out of line of sight when there's nobody on a facility are there baby steps in terms of improving performance and proving yourself. Okay.
Brilliant. That was a very detailed answer. Thank you very much, Maurice. I think, Jacinto, do you want to ask a question as well?
Yeah. This time, instead of writing, I just would like to ask a question directly through the voice. And thank you very much for this great presentation. Since we are discussing about operators, and I really care for the topic of teleoperation, I would like to ask you, when we are using rich sensor systems like yours, let's say, where does their computational burden could limit the real-time teleoperation, in your opinion, the most crucial situations? Because I think it's heavy. I mean, the computation should be quite heavy.
No, I guess we've always developed a system to run in real time. Maybe what we found with some of the more, like we've developed systems that do semi-automated path planning, so identifying which terrain is flat to allow a remote operator to choose between go left, go right, go straight, And adding that extra perception system does start to require our mapping system to be more efficient, because you're still limited by the one compute box. But the latency of computation is I mean, everything is running in real time on board. I think teleoperators who want to make decisions in these very complex environments face challenges with bandwidth more than the mapping latency. So being forced to operate with maybe 1 Hertz images, or images that have been highly compressed, for example.
Okay, thank you very much.
Okay, thank you.
So I think we've got a few more questions in the chat, but maybe I'll save them for the final panel discussion, so we can have some time for Carl now to take the stage. And thank you very much once again, Maurice.
Okay, thank you for inviting me.
Thanks. Can I just check I'm sharing the slides?
Yes, we can see it, yeah.
Okay, thank you. Okay, so I'm going to be talking a bit about a particular project that we've done over the past 4 years. But first I want to introduce the center that I work in. So it's the Center for Defense Engineering Research and Training. We've got a number of components, and there one area is on maritime autonomy, which is my area of interest, and then there are other areas as well which interrelate with the work we're doing. And of particular note, we've got the AI/ML and also bio-inspired sensing. And we've got about 12 academic staff in the group currently, growing, and about 5 postdocs and 16 PhDs and some RAs. Okay, in terms of what we do, we predominantly work on uncrewed surface vehicles and underwater vehicles. We've got 2 examples of vehicles that we have at Flinders here. We work on both the hardware platforms, purely because we want to be able to develop the platforms to suit our needs. If we go and buy an off-the-shelf platform, then we're usually bound by the manufacturer's restrictions. So that means limited computational power, as Maurice was talking about before. You were actually stuck with what they give you. Also looking at enhanced trusted autonomy. So we want to be we want the vehicle to be able to provide an explanation as to why it made a certain decision. One project that we have currently is generating a narrative from the mission log, but also then looking at getting a live narrative as the vehicle progresses, and to provide reasoning as to how it's come to a certain decision. Looking at autonomous decision making using multi-objective optimization, particularly useful for mission planning, where we have multiple agents and lots of tasks and lots of disturbances in the environment, limited fuel, so the vehicles have to be able to decide how they're going to complete their mission, and if vehicles fail, for other vehicles to take over. Looking at the use of machine learning, reinforcement learning to control systems, particularly where we have vehicles operating in high sea states, or they have damage caused to the actuator or even to the platform itself, and allowing the vehicle to be able to change its thruster allocation to be able to complete its mission. And looking at the use of bio-inspired signal processing to improve the capability of autonomous vehicles to see using acoustics or using optical in highly turbulent environments. Some of the projects that we have been going for a few years. So looking at the use of uncrewed underwater vehicles for ship hull and subsea platform inspection, in particular looking for biofouling on ship hulls or on platforms out at sea, and vehicles to be able to remove the biofouling as well. And then other vehicles, such as the one I'll present today, looking at detecting mines in the surf zone. We've been working on autonomous launch and recovery systems for extra large UVs, working with smaller uncrewed underwater vehicles, and also for guidance systems to allow underwater vehicles to enter into a torpedo tube or a docking bay of a larger vessel, such as a submarine. And again, working with guidance systems for underwater docking with static and also towed docking stations. And then on the surface vehicle side, one of the larger projects we have is looking at collision avoidance regulations compliance, the rules of the road, basically for unmanned surface vessels operating in proximity with other manned and uncrewed vessels. That's becoming extremely problematic. And mission planning and coverage scanning for harbors and coastal areas. Okay, so I'll come to the project that we're talking about today. This started back in 2019. We were tasked to do a project looking at mine countermeasures in the surf zone. So by the surf zone, I'm being, if you look at the closed inshore area of the beach, going from the beach surf waterline out to about 50 meters depth out at sea, and looking for mines that are buried just below the sand or lying on top of the seabed. We're not looking at mines that would be hanging in the water, close inshore, that'd be lying on the seabed itself. And the objective was to be able to allow a task force to insert an amphibious group onto the beach, and rather than use Navy divers to go and reconnoiter and look for the mines, to use robots to do this. And the reason being, the surf zone is actually quite dangerous, especially for humans to operate in, as well as for robots. The other thing, so the group was led by Thales here in Australia. It was funded by the Trusted Autonomous Systems, Defence CRC, Australian government initiative. We worked with a number of companies, but also with other universities. So aside from Flinders, we had Sydney University, Western Sydney University, and University of Technology Sydney. And if anybody knows the map and the location of these universities, all the entities are on the East Coast, and Adelaide, Flinders University is based right in the middle in the south of Australia, which made transporting things around the place quite difficult. Okay, so why is it a challenging environment? Firstly, as I mentioned, the mines are located on or below the seabed. I should have written down here, the seabed is particularly flat, so there's hardly any features on it. So using something like SLAM is actually quite difficult to use successfully. The next thing is that the surf itself is quite powerful. High breaking waves, typically up to 1 meter and even more than that, coming right up onto the shoreline. It makes it difficult for free-swimming UUVs, standard uncrewed underwater vehicles, to maintain position, pose, and trajectory. And it's relatively easy for these underwater vehicles to get tangled up, damaged, or to ingest foreign objects in the thrusters. And we saw that happen in some of the trials that we had with some of the vehicles that were fielded. The environment is very turbid. So we saw the example before that where we had snow in the environment. It's very similar. So we have a lot of sand particulates. In our case, we have seaweed, we have bits of jetsam rubbish, and we have entrapped air bubbles in the environment. So that makes it difficult to use a camera and the LiDAR, but also the entrapped air bubbles make it difficult to use a sonar. And I'll show you some of the images. Coupled with that, the water is quite shallow, so less than 50 meters with wave action. So we get acoustic multiparting of the acoustic signal, whether it's for an acoustic modem or for an ultra-short baseline, a USBL. We get a signal bouncing between the surface and the seabed many times, which causes a lot of problems in communicating successfully. When we're in about 3 meters of water, you're lucky to get 100 bits per second for the communication. And also really difficult to get any localization using ultra-short baseline. Okay. This is the concept of operations. So we have the seabed at the bottom there. We have a number of vehicles in there. We have two hovering type torpedo-shaped vehicles. These were developed by the University of Sydney. Their objective was to swim through the environment using downward-looking cameras and eventually even sonar to look for objects, anomalies on the seabed. Once they detected something, they were then tasked to send that back to the mission planner, which was sitting in a buoy on the left-hand side over there. And that then communicates with the crawler vehicle that we developed to go and investigate up close. Now that buoy can communicate with a shore station or with a ship station, allowing the mine clearance officer on board the ship to be able to determine whether what the crawler is looking at is actually a mine or something else. We can't just simply neutralize the mine. We have to get a okay from a mine clearance officer before we can do that. Now, the downside of the vehicles doing the scan of the area and going back to the ship to report what they found, then something else coming out to neutralize the mines, is that the relocalization is quite problematic, especially where we have a very flat surface. So if you can have the vehicles themselves passing the location of the anomaly directly to the crawler vehicle at that point, it simplifies the process significantly and speeds up the process of neutralizing the mine. Okay. So this is the crawler that we developed. Bottom left is a crawler that we started working on with the University of Bremen. We use one of their designs that actually was developed for working in 5,000 meters depth of water. It's particularly heavy, which is great for the surf zone because the waves don't knock it around. So they gave us, they built rather the chassis for us together with the host control for the vehicle. And then we worked on the payload control side for the vehicle. We then modified that, fitted on our sensors onto it. And what you see in the middle is the vehicle that we fielded over the first 2 years of the program. You can see that there's a strange looking object on top. That's a buoy with a tether going back into the vehicle. And as the crawler moves out to sea, the buoy comes up and it communicates back to the crawler via the tether, but also with the shore station or the ship station via RF and long-range Wi-Fi. On top of the vehicle, you will see a number of sensors. If you look at the vehicle on the right, which is the last step in the evolution when we finish the project, you see that the vehicle carries a camera up top. Below that is a multi-beam sonar. It's one from Blueprint Subsea. And then to the left of that is the ultra-short baseline and modem combination from Advanced Navigation. The other thing that the vehicle's got there is it's got an arm holding a mock neutralizer. So once the vehicle finds the mine, it then drops the neutralizer next to it, marking where it's dropped it. Okay. In terms of the sensor suite, so we have position and orientation from the Subsonus ultra-short baseline, which is relative to the surface tracker buoy. The tracker buoy contains a GPS, so the USBL communicates, takes the GPS and then sends the position fix to the crawler vehicle. We have a depth reading from the pressure sensor on board the crawler. We have track odometry, and we also have a Doppler velocity logger, which measures angular and translation velocities below the vehicle relative to the seabed. So this sits about 5 centimeters above the seabed on the bottom of the crawler. And then in this case, we used an extended Kalman filter to fuse together data and to provide the coordinates of the crawler and the velocity of the crawler. Okay, so in terms of the localization, you can see that the GPS, which is mounted on the buoy, it's if you look at the yellow marker around this position, is the position accuracy is quite low. We then, as I mentioned, fuse that with the Doppler velocity logger, the magnetometer, and the track odometry, and we get a much better position fix. and postfix. So the vehicle starts off from the right-hand side, moves across, then reverses backwards, and then moves forward again in this case. I should point out that the outer short baseline here wasn't much use in the 3-meter depth of water because of the multi-plotting problem. So it's one of the lessons that we learned that although there's a variety of sensors you can use for underwater navigation, they are really limited in terms of working in certain depths of water and environments. Okay.
Carl, if I
next part,
can, just 1 minute, if you can wrap up in 1 minute, so we have some time for the final panel discussion. Thank you.
Yep. This is an example of a manta mine on the left. On the right, that's seen with a camera. On the right is a sonar image of the mine. This is a good day to see the mine. This one is not a good day to see the mine. So this is a very turbulent environment during a storm event. And we had all our vehicles operating in storm events on every single field trial. So you can see the mine in the middle over there, but it's very difficult to distinguish it clearly. On the right, the sonar image to the left is the raw sonar image. On the right of that is a processed sonar image, and now you can begin to see the shadow above the mine over there. And I'll show you what I mean in a second. So here's the images from the sonar. We've processed the image on the left. On the right, we have highlighted the shadow using filtering techniques, and then we found the leading face of the mine because it's from the length of the shadow, we know how high the mine is above the seabed. And then the front of the mine will be brighter than the rest of the shadow behind it. Okay, so the vehicle is able to see the mine. We have also used bio-inspired signal processing techniques, and I'll show you quickly. This is a video. On the left is the raw video from the UKRAS sonar. The middle two use particulate-driven signal-to-noise ratio filtering. The one in the middle shows averaging across all the beams. The one we're injecting sand into the environment ahead of the mine, ahead of the sonar at this point, and you'll see it wipe out. The one on the right, we're doing filtering on individual beams, and the sonar has 512 individual beams. And you see that the one on the left, we cannot see the mines any longer. The one in the middle, the average, we start to lose the mines. The one on the right, we can still continue to see the mines. I'll skip past this. Okay, so this is the full team with all the vehicles. The two seeker vehicles on left and right are from Sydney University, and the crawler vehicle, which weighs about 380 kilos and about 1 meter by 3/4 of a meter. There is one that we developed at Flinders. We are still continuing to work at Flinders on this, and instead of being able to just restrict it to launching from the beach, we can also now launch it from ship. So we've added buoyancy tanks, variable buoyancy tanks, and we're going to add thrusters to allow the vehicle to be launched from a ship, go down to the bottom, or go to neutral buoyancy and swim around obstacles to get to its target. Okay, Gianmarco, that's it from me.
Amazing. Thank you very much.
Okay.
I think we've got probably time for one question, and then I want to ask the panel to sort of rejoin, everyone from the panel to join and have a very quick panel discussion. I guess since I can't see any in the chat yet, I'll ask it myself. So is there any thoughts on your system on how to handle or not disturb the local fauna? Because I'm assuming you go into sort of the sea and then there's going to be lots of fish, but also equally how the local fauna might disturb you, because I know that fish are very curious animals, so they might come and have a look at what's happening. How do you handle that?
So yeah, we've had problems, especially with the surface vehicles that and the animals coming to the surface vessels. Underwater vehicles, particularly the crawler, not so much of a problem. They tend to swim out of the way, but we have to be cautious, especially about seagrasses down here in Australia. There's a lot of work to rebuild seagrass seabeds, and we were careful to choose tracks on the vehicle that do not damage the seagrasses. But we also try and stay out of those areas.
Okay, perfect. Thank you very much. I think I'm gonna steal now just to open a panel discussion, which might have to be a very quick one. I might steal Rob's question that he asked Maurice, because the idea of the ethos of this webinar series is to sort of create links and understand how we can better collaborate with each other. So I think Rob asked, if there's sort of open days, particularly in that case it was Oxford, but I'm going to ask to like sort of the other institutions as well, maybe not necessarily in-person open days, but is there an opportunity for us, for people from the UK to come and see, mostly virtually in the case of Australia and Canada, what you guys do? So I'm going to start with Maurice first. I think you quickly answered that on the chat, but if you want to expand on that, please.
Yeah, I guess we're hosting an industry day on the 25th of September, which coincides with the 10-year anniversary of Oxford Robotics Institute. So if you're interested in attending, just drop us an email. Okay.
Perfect. Francois, what about yourself?
So on our side, we don't have open days, but we are opening our testing facilities to any researchers. So they can just write me an email and we can host them in the remote location. So we can cover the cost of hosting at the remote location.
Perfect. Is it worth mentioning, Francois, that you're currently in the UK right now? So maybe if anyone wants to reach out, this is the best time to do so.
Also a good opportunity. I'm the UK. I will try to do a tour with a similar length presentation. I will be in Manchester March 20th, I think, and try to move around maybe in Bristol, and I can pick any invitation. Actually, I'm around to make contact.
Perfect. And Jacinto, before you, Carl, do you want to answer that?
I just wanted to invite you in Bristol too, Francois.
I'm planning
Be
to.
ready.
I'm looking at it.
Exactly. My colleague Marianti Leon mentioned this the same. I would like to ask a general question, a really general
sorry,
one.
Jacinto, before we move on,
Okay.
I think Carl, maybe if Carl wants to answer that, and then you can move on. Sorry. What about yourself,
That's okay.
Carl? I think.
We don't have formal open days, but we have visitors coming all the time. We also have opportunities for staff from other universities to come over as distinguished research visitors for a couple of months or so to do some work with us. We take quite a few interns from France through relationships with Enston over there, and also from the UK.
Brilliant. Perfect. Sorry, Jacinto, off you go.
Yeah, don't worry. So, according to several reports, for example, from the UK government, the workforce skill gap hinders robotics adoption. I would like to ask you, each one of the speakers, does this barrier also significantly limit the deployment of robots in extreme environments, and consider the environments you specifically target, the workforce skill gap? Having specialized users and specialized technicians and engineers and researchers also.
So, if I may start, or all right, okay. It's a tough question for researchers. So clearly, our job is to highlight challenges and find solutions. And like Maurice wrote in his answer, is that transferring a very complex and expert system up to a usable, I would argue that is a higher TRL research, and there's probably better skilled people than us to do it. That being said, it's not like just transferring the problem to others that we should help and connect well to those higher TRL, but it didn't really where the researcher are positioning themselves in finding problems essentially.
Yeah, I think companies that are providing maybe services for robot inspection, for example, or really only in a position to deploy fully commercial solutions, and you do see these valleys of death where even just proposing from an academic perspective a solution is an uphill struggle, that it does have to be flipped out into a company to get the proper respect from the commercial sector as well. Before you can start talking about workforce, you need to work with like supply chain and understand how large operator companies actually take on products into their portfolio, for example. So it's not just about the end operator worrying about their job being displaced. It's about how it's actually taken up by industry.
Yeah, I agree with that comment. I think the biggest problem we face is it's very difficult to show industry that we can come up with a better solution. They still see academia and researchers as being perhaps that the solutions are a bit more fragile, not yet proven to go into the field. And the other thing we have, and I imagine this is a common situation around the world, we find that our graduates, our postgrads are being snapped up very quickly by industry, which makes it even harder then to keep on building up momentum in the area.
Thank you very much.
And also
Thank
labor
you, yeah.
shortage is a problem probably at the task that we want to automatize. So labor shortage is everywhere. So that situation is probably larger than just using a complex robotic system.
Thank you.
Yeah, absolutely. Yeah, that's a huge issue everywhere, I guess. Perfect. I think we're very over time. So I would like to thank the speaker once again for joining today. Really, really interesting talks. And I would like to thank the audience as well. Thank you for engaging and thank you for joining us today. This event has been recorded and will be posted on the UKRAS YouTube channel relatively soon. So it'll be able for people to rewatch it. And yeah, I think I can just end it here. Thank you very much, everyone.
Okay, thanks, Marco.
Thank you.
Perfect.
Thank you.
Thank you.
Cheers,
See you later.
Thank you. Bye.
Yeah.